Hi everybody, Mrs. Pesic here. We are looking at Chapter 3, Exponential and Logarithmic Functions. Section 3.1 is called Exponential Functions and Their Graphs. Your learning objectives are to recognize and evaluate exponential functions with base A, graph exponential functions and use the one-to-one property, recognize, evaluate, and graph exponential functions with base E, use exponential functions to model and solve real-world problems. Okay, so let's take a look at first of all, at our definition of exponential functions. The exponential function f that has base A is denoted by f of x equals a to the x. A has to be greater than 0 and it cannot equal 1. And x can be any real number. So my first question for you is, why can't the base be equal to 1? Well, if we had some function that was f of x equaling 1 raised to the x, no matter what we plug in for x, would the function value ever change? No, because 1 to the second is 1, 1 to the third is equal to 1, 1 to the fourth is equal to 1. So we do not allow the base to be 1. But the base can be anything between 0 and 1. So something in this interval from 0 to 1, if I'm going to use interval notation, union with 1 all the way to positive infinity. So your base can be any of these numbers, from 0 to 1 or from 1 to positive infinity. A little recall about exponents. You know that 4 to the third is the same as 4 times 4 times 4. You've also learned that 4 to the 1/2 is the same as the square root of 4, which would be equal to 2. Okay, so we've handled integer exponents and rational exponents, but what about irrational exponents, like 4 raised to the square root of 2? Well, square root of 2 is about 1.414, so you know that's going to be close to 4.1.4 or 1.41 and so on. All right, so you can use a calculator to evaluate each function at the indicated value of x. So f of x equals 8 to the x, where x is equal to pi. So if you wanted to evaluate that, you're really trying to find f of pi, which would be, in this case, 8 raised to the pi power. Your calculator will be happy to help you with that. So if we go to a calculator, and let's say we want to go to, let's see, I'm just going to go to Scratchpad page, and I'm going to do 8 raised to the pi. I need my pi button. And I'm doing Control Enter so I can get a decimal approximation. So 8 raised to the pi power is going to be about 687. All right. What about 8 raised to the negative x as our function, where x is equal to 1/2? Well, f of 1/2 would be 8 raised to the negative 1/2. Now, you know that's the same as 1 over 8 to the positive 1/2. And if we want to use our calculator for this, 1 over 8 to the 1, and that's the same as 1 over the square root of 8. So we can do that on our calculators. That's not what I wanted. I can do 1 divided by the square root of 8 and get a decimal for that. Or I could have just done immediately 8 raised to the negative parentheses 1/2 power, and approximately equal to 0.353. All right. Okay, let's skip that last example and move on. So graphs of all exponential functions are going to have similar characteristics. So if we sketch the graph of f of x equaling 3 to the x, and g of x equaling 5 to the x, they're going to have some similar features. Let's plot a few points for x versus f of x. So for example, if I plug in -2, -1, 0, 1, and 2, if I plug in -2, that's 3 to the -2 power. That's going to be 1 over 3 to the second. That's 1/9. If I plug in -1, that's 3 to the -1, which is 1/3. If I plug in 0, I get 3 to the 0, which is 1. If I plug in 1, I get 3 to the first, which is 3. And I plug in 2, I get 3 to the second equals 9. Remember, anytime you need to pause this video, if I'm going too fast, feel free to pause and stop or rewind. All right, so if I'm going to plot these points, -2 goes to 1/9. That's just barely above the x-axis. Negative 1 just slightly higher than that, that's at 1/3. 0 goes to 1, 1 goes to 3, and 2 goes to 9. So my graph is going to be starting out really low here, and it's going to slowly be rising, and then it really starts picking up and getting very fast, very quickly. This is an exponential growth type of function. All right, if you hear about something is growing exponentially, that's what they're talking about, this kind of a function. What about x versus g of x? Now if I plug in negative 2, negative 1, 0, 1, and 2, negative 2 would be 5 to the negative 2, and that's 1/25. If I plug in a negative 1, I get 1/5. I plug in a 0, I get 1. If I plug in a 1, I get 5, and I plug in a 2, and I get 25. So if I'm going to graph this one, negative 2 goes to 1/25. That's even a little bit lower than the first one. 1/5 is a little bit lower than the other. And then right there, spot on, they actually meet right there at the order pair 0, 1. 1 is at 5, and 2 is way up here somewhere at 25. And so again, this graph is going to look very similar, but it is actually rising more steeply. All right. So what do they have in common? What can we say about these two graphs? They're both increasing, although g of x is increasing more rapidly, and both graphs are continuous. All right. What if we were going to graph 3 to the negative x or 5 to the negative x? All right. For this one, if we're going to graph capital F of x as 3 to the negative x, let me put this side in blue. So if I'm going to do capital F of x is 3 to the negative x, remember that's the same as 1 over 3 to the positive x, which is the same as 1/3 to the x. Remember we said that that base can be between 0 and 1, or it can be greater than 1. In this case, the base is between, this base here is between 0 and 1, right? And so in that case, that graph is going to look a little bit different. We're going to plot that. So if I graph x versus capital F of x, I've got, let's do negative 2, negative 1, 0, 1, and 2 again. So if I have 1/3 to the negative 2, that's the same as 3 to the positive 2, so that's going to be 9. 1/3 to the negative 1 is going to be 3 to the first, which is 3. 1/3 to the 0 is 1. 1/3 to the first is 1/3. And 1/3 to the second is 1/9. So what's happening when we plot these? Negative 2 is up here at 9. Negative 1 is here at 3. 0 is at 1. 1 is down here at 1/3. And 2 is at 1/9. So this time the graph is looking like this. This time it is a decreasing function. As we go from left to right, the graph is falling. And likewise, if we were to plot this one, 5 to the negative x, do that one in red here, I'm going to graph this one. It's going to be the same thing, except it's going to be falling even steeper. So it's going to look something like this. We won't go through plotting all those plots. All right, so both functions are decreasing, and both these functions could be rewritten with positive exponents, which is what I just did. So in other words, instead of writing 3 to the negative x, I rewrote it as 1/3 to the positive x. I rewrote it with a positive exponent. All right, so notice that f of x equaling 3 to the x and capital F of x is 3 to the negative x, remember, which we also said that was going to be equal to 1/3 to the positive x. They are reflections of each other over the y-axis. All right. Okay, in general, y equals a to the x has one y-intercept and one horizontal asymptote. The exponential function is also continuous. So if we're talking about an exponential function, y equals a to the x, let's say it was an exponential growth function, as opposed to these, which we would call exponential decay. These were exponential decay functions, and over here, these were exponential growth functions. All right, so let's go back to this for a minute, and notice that in general, these are going to have one y-intercept, and they're going to have one horizontal asymptote, which in this case, for this particular one, was just y equals 0. All right. Does an exponential graph pass the horizontal line test? Sure. Any horizontal line I draw will go through the exponential function, whether it's an exponential growth or decay, in at most one point, which means that exponential functions, their inverses will also be functions. All right, and it's a one-to-one function. All right, so if we were going to solve an exponential equation like this, if we have 16 equals 2 raised to the x plus 2, one way that I would like you to be able to solve this is to get both sides to have the same base. Right now, this base over here is a 2, this base over here is a 16. But since 16 is 2 to the 4th, I can rewrite this as 2 to the 4th equals 2 to the x plus 2. All right, because this is a one-to-one function, there's going to be only one number. If our bases are the same, then our exponents must be the same. So I can just set 4 equal to x plus 2 and solve. Subtract 2 from both sides, and I get x equals 2 as my solution to this equation. And if you want to test it, plug in 2. Is 16 really equal to 2 raised to the 2 plus 2? Like 16 equals 2 to the 4th? Sure, that works. So we like x equals 2 as a solution to this equation. All right, what if we try this one? 1/3 raised to the x equals 81. Well, can we rewrite this so it's rewrite 1/3 as 3 to the negative 1 raised to the x has to equal 81? And that means that's really 3 to the opposite of x, because I'm raising a power to a power, so I need to multiply these. And if that's the case, can we get both of these to have the same base? Well, 81 is 3 to the 4th. And so if 3 to the 4th is equal to 3 to the negative, I'm supposed to say 3 to the negative x, if my bases are the same, then my exponents have to be the same. So I get negative x equals 4, divide both sides by negative 1, and I get x equals negative 4 as my solution. You could plug it back in to your equation and show that it works. All right, so let's take a look at this. We are going to describe the graph as a transformation of a parent function, f of x equaling 4 to the x. So if this is our parent function, and we know what this looks like, this f of x equaling 4 to the x is going to look very similar to these graphs. As a matter of fact, it's going to be kind of something right in between, right? It's going to go right through 1, 4, and so on. So it's going to be an exponential growth function. Get back to my page. Okay, so what about 4 to the x minus 2? How would that graph have changed from the original? Well, let's take a look at this. We know that we have an x minus 2. We're subtracting 2 from the x. Is that a shift, a stretch, a reflect? Well, this is going to be a shift. Is it going to be a shift up, down, right, or left? Well, if it's x minus 2, it's going to be a shift to the right 2 units. Let's test this and graph this on our calculator to confirm this. So I'm graphing the parent function, which is 4 raised to the x. There's my parent function. And now if I graph 4 raised to the x minus 2, then there's my same graph. It's been just shifted to the right 2 units. Let's take a look at the next example. What about opposite of 4 to the x? Remember, if you have an opposite in front of your entire function, then is that a shift, a stretch, or a reflect? Well, it's going to be a reflection. It's going to be a reflection over the x-axis or the y-axis. If we're making the whole function negative, like we are here, then it's going to be reflected over the x-axis. If you make just the x negative, like if we just made that negative x there, then it would be a reflection over the y. So let's confirm that with our graph. If I go and I type in, let's see, I'm going to graph opposite, no, let's see, I want to go tab. I want opposite of 4 raised to the x. And there's our reflection over the x-axis. All right, and what about this one? This one says negative 1/2 times 4 to the x. Well, that graph is going to look this graph's going to look just like this one, except we have this 1/2 here. So what's that 1/2 going to do? Well, if your function is getting multiplied by 1/2, then that's going to be a vertical compression of 1/2, along with the reflection, because we still have that negative in front, right? So along with that negative, it's going to be reflection over the x-axis. So let's see if that is true with our graph. Opposite of 1/2 for the x. So I'm going to put on here, I want negative fraction template, 1/2, and I want times 4 raised to the x. Okay, so it's been reflected over the x-axis and it's been vertically compressed, meaning it's getting closer in towards the x-axis. It's vertically compressed towards the x-axis. All right, and okay, what about this one? Well, here we have that negative being multiplied by x itself. Remember we talked about that just a minute ago? That's when we're going to have a reflection, but it's going to be reflecting over the y-axis. And the +3 here, is that going to be a shift, a stretch, or a reflect? That's going to be a shift. And since it's after the function, not in with the x, it's just a shift of 3. So let's confirm that with our calculator. I want 4 to the negative x plus 3. Let me add a new page here. Graphs, clear out this ink. So I want my parent function, which is 4 raised to the x. So there's my parent function. And I wanted to see 4 to the negative x plus 3. So I'm doing 4 raised to the opposite of x. And then I'm going to get out of that exponent and do a +3. All right, so what do we see? We see that it has been reflected over the y-axis. Let me confirm that by just doing one more. 4 raised to the negative x. All right, that's our reflection. There's my original, and this is my reflection, and then it's also been shifted up 3 units. All right, so that concludes our first part of the 3.1 video.